Okay, hello class, this is Mr. Chase, and I'm sorry to be out today, but I'm interested in sharing a few of my thoughts about SLT 16 with you today. And so hopefully you've had a chance to look at this warm-up, and if you haven't, then pause this video and make it happen, and we'll be back together in just a minute. Okay, have you had a chance to take a look at this warm-up? This task, at least especially part A, and well, B too, should seem very, very familiar. It seems like something we would have done maybe on the very first day when we studied exponential growth. Does it ring a bell? What we did, if you'll remember, we came up with that exponential model before you did anything with exponential models, and the model I think we came up with was like 4 times 2 to the x, or something like that. And one task that was really interesting on that was this idea that we could not just express what the growth rate was every hour, which was, I think, doubling, right? It was times 2 each hour. But we asked you an even deeper question. We asked you, what's it doing every half hour? What's the multiplier? Or what's the growth factor, you might say? And so that's very similar to what we're doing here. I'm just telling you, if you haven't already observed it, that we're tripling every hour. And you can see that in the table. As we increase t by 1, P of t, or the population, is tripling. I think that's pretty clear. And so the deeper question comes, and here it is, what's the growth rate every half hour? And I tried to model this actually after our first task, that first day of exponential growth. I'm asking you to kind of fill in the gaps. What would you have to do to get this value, this halfway point? We realized that on that day that it wasn't just the average. It's not going to be like 20. It's not just the average, because that assumes kind of linear behavior in between, and we know that's not quite right. We've been through that. So what is it that gets us there? Whatever it is that gets us there, we need to have a constant multiplier. If there's going to be a constant multiplier in the big table, when we kind of, I don't know how you want to say this, when we zoom in on it, we should also have that property still true, that like kind of the hallmark of exponential growth, that there's this constant growth ratio always. So let's say we don't know it. This is the approach we took on that first day. Let's say it's some unknown number r, the growth rate r. Well, we don't know what it is that gets us from this value to this value to this value here. We do know that if we take 10 and multiply by r twice, we get 30. Yeah? So that is to say, 10 r squared is equal to 30, which means that r squared needs to be just 3. That is, if we multiply by this unknown number twice, it should be just the same as if you multiply by 3. It should be the same thing. So what is that number that must be what r is? Well, it must be root 3, right? It must be the square root of 3. And sure enough, if you multiply by root 3 and then by root 3 again, you do, in fact, you really are just multiplying by 3. If you multiply something by root 3 and then root 3. Great. Wonderful. So what about B? What about every minute? What do we have to multiply by if we want to grow the population by the appropriate amount for only 1 minute's worth of growth? Well, again, we could apply the same logic. We're going to multiply by r how many times? Well, in the course of an hour, we need to multiply by this unknown multiplier 60 times. Okay, so I think I'm ready to say it, right? We're solving this equation, right? I'm going to multiply 10 by r, whatever this r value is, 60 times. And I should obtain, in the end, 30 again, just like the last part A that we just did. So I think we can just jump right to the answer, and maybe a lot of you just already did. It's the something root of 3. Well, it's not the square root this time, though. What is it? That's right, I hear you say. It's the 60th root of 3. I know that's kind of a crazy number to even write down, but that's exactly what it is. It's the 60th root of 3. So like I said, there's no need to fill in these tables, but if you'd like to, then you would just multiply this number by the 60th root of 3, and then do it again and again to get to the next cell. And after having done that 60 times, you would in fact be at 30. That would be multiplying by the 60th root of 30, the 60th root of 3. If you do that 60 times in a row, it will be having you having just multiplied by 3. That's all it will be. Great. That sets the stage very nicely for SLT 16. So let's take a look at this first resource. It's titled at the top, Manipulate Exponential Models to Reveal Information, Guided Notes. So that's what it says at the top. And I don't normally spend like a ton of time going over the standards, but I actually do want to take a look at what this says here. I kind of sometimes skim over the screen. But this is going to come back in an important way in a little bit here. It says, produce an equivalent form of an exponential expression to reveal percent rate of change. So let's see if we can, and maybe we'll even come back and highlight this later. This is kind of the important standard. This is a very interesting standard, so I just want to maybe come back to it in a little bit, because it's a little strange what we're going to be doing today, but it ties in with what we did in the warm-up. So take a minute with your group to look at example 1 and really the 3 questions here that are presented for you, and then we'll come back together in just a minute. If you need to pause the video, that would be great. Okay, are you back here? So it says if you start an experiment with 2,000 bacteria cells, perfect. We've just been doing that over the last day, and an hour later there are 2,880 bacteria cells. Write the exponential model for the number of bacteria for T hours. So there are a number of ways you could reason to what the growth rate is over an hour. So maybe we should share out even from people out in the class. I don't know, maybe there are a couple different ways to do it. But here's, I think, the most efficient way. Feel free, like I said, to have a discussion first if you want to do that before I give it away. But it's just like if I ask what portion, what do I have to multiply? What is it that I have to multiply 2,000 by to get 2,880? What do I have to multiply by? Well, don't think too hard. How about this? Right? Asking, what do I have to multiply by in order to get something else? That's just division. Isn't that our name for division? So think with me here. If you multiply this thing right here by the number 2,000, am I right? Do you not get 2,880? Think about that for a second. Right? What do I have to multiply 2,000 by in order to get 2,880? It's just like saying, what do I have to multiply 3 by to get 7? Well, maybe we don't know, but isn't it 7/3? Right? Isn't it just whatever makes the job happen? So it's the same thought here, isn't it? It's just asking, what is it that I have to multiply by in order to get 2,880? So apparently this is how much it grows each hour, by this factor. So I think we can write our model. This is like our B value, right? This is like our B value. That's our growth factor, or I guess I call it R up here. Let's change it to B. All right, so it's the B factor. It's the growth rate, or the multiplier, whatever you want to call it. And what's the initial population? Well, it told us it's 2,000. So you're ready to write a model for the number of bacteria there are after T hours, and that's important, hours. Let's call it maybe P of T. We get to name our own functions in math usually, so let's name it something meaningful. So this will be P for the population of bacteria after a time T measured in hours. So we'll write A times B to the T, 2,000 times 2,880 over 2,000 to the T. Now, I hear you say, that seems like a weird way to write it. Let me grab my calculator here. If you would like, that's actually a perfectly good way to write it. But here's my calculator. You could also write that if you do that division, it's 1.44, and that's not even rounded. That's perfect. Okay. Well, I guess you don't need a calculator for that, do you? It's just 288 divided by 2 followed by divided by 10 3 times. So whatever, that's a great way to write it. Let's write it that way. I think I like that. In the box, that's great. And then before you leave this section of the board here in this problem, let's just verify that it actually works. If you plug in 0, do you get 2,000? Try it. If you plug in 1, do you get 2,880? Try it. And That is to say, is this model seem to be doing what we claimed it would do? It doesn't work. And the answer, I think you can see if you check it, it will work. All right, so then here's the question. An amount that changes by a fixed percent each time period can be represented by the model. What do they want us to put in there? An amount that changes by a fixed percent each time period can be represented by the model. I think they want us to say, well, actually, I'm not prepared to actually answer that yet. All right, so let me pause before we say that yet, right here, because I don't know if I'm ready to I don't know if you're emotionally prepared for what I'm about to tell you there. If I told you that you got or how about this? Your bill at the restaurant was $2,000. It's just like a big party, okay? Just go with me on this. It's like a huge party. And you paid $2,880. That is after the tip. My question is, what did you just tip? That is, what percentage did you just tip? How generous were you? Keep in mind that like a generous tip is usually around 20% or so, right? But what percentage did you tip above and beyond what the meal cost? It was $2,000. What did you tip? What percentage did you tip? And actually, if you want to work that out real quick, maybe I'll throw that back to you. You can pause the video if you like. Figure that out. What was the tip? If you paid $2,880 on a $2,000 bill, clearly the tip was $880. So what percentage of the bill was that? Okay, if you've had a chance to think about that, one way to write that would be to say, okay, well, I paid this much plus this much, right? So I paid like the whole bill. This is like the whole bill right here. But then I also paid this like extra bit, this tip. So what percentage of 2,000 would that be? That is like, if you scored 880 points on a 2,000 point test, what did you score? What percentage did you score on the test? Now, as soon as we do this, we don't need to do this ever again in your life, right? You'll notice right away that what you get is 1 here, of course that's 1, but here you get 0.44. You got a 44% on your test. Okay, well let's go back to the tip model. That's a terrible test score, but it's not a bad tip, is it? What did we tip? We tipped 44%. So hopefully you see that 2,880 represents a 44% growth on the original amount of bacteria cells, which was 2,000. So it's gone up by 44%. So do you need to go through this logic every time you have that conversation with yourself? Well, you may, but it should just be apparent over here from the equation that that's what the growth rate, the percentage growth rate is. So now I think I'm finally ready to say what this model is down here, right? And I'll use P just because that's what we've been doing. But there's nothing special about P. We have some amount that we start with, A, times 1 plus, well, whatever our percentage rate is, right? Here it's like 44% to the T. So in our case, so just so we understand what this R means here. R, we mean the percent growth rate. Hopefully that's clear. How can we change the model to represent the bacteria per minute? Oh, well, we've just talked about that earlier on the last slide. If we're growing by a factor of 1.44 every hour, what is it going to be per minute? And again, I actually really want you to think about this. Go back to the warm-up if you need to. Pause the video, and then we'll just write down the answer in a minute here. Okay. Are you back? All right. So I think it should be clear from our discussion in the warm-up. I won't go through exactly why here. That it should be the 60th root of 1 0.44. Isn't that what it grows by per minute? Okay, so that's how much it grows per minute. Another way of writing that would be, as you know, 1.44 to the 1/60th. And the way we would write that as our original equation, we can actually rewrite our original equation using this idea. It's still 2,000 is of course how much we start with. But we could actually write whatever this is, the 60th root of 1.44. That's the growth rate per minute. But then if we still want t, if we still want t in hours, then we need to write the following. So keep in mind that if we have 60 minutes, then we want to be at the place where we are at 1 hour. So so what do we need to do up in this exponent here? If we have like every hour, how many minutes is that, right? Like so, clearly I can't just have a t there. What do I need? Let's see. Well, how about a 60t? Well, let me just play around with that and see if that makes sense. Well, if we put a 60t in there, is this doing what we want? If we put in t equals 1, for example, then the exponent up here will be 60. And yeah, that makes sense. We'll actually have gone 1 hour. That's 60 minutes. The growth rate of the 60th root of 1.44. By the way, I'd like to know what that is. The 60th root of 1.44. I'm going to do that on my calculator here. And I get 1.006. So I'll write this approximation here. So it's approximately 2,000 times 1.0061, say, to the 60t. So see what we've done there is we've put this in terms of the t is still in hours, but now we can see, just looking at the equation, we can see what the growth rate per minute is. And in fact, can you tell me what the percentage growth rate is each minute? The percentage growth rate? Think about what we wrote up here. Well, we're growing at, if this is 44%, what is this down here? Is that 61%? Is that 6.1%? Or is it a growth rate of 0.61%? I think that's what it is. It's a 0.61 growth rate per minute, right? So notice how this is different. Over the course of an hour, we're growing at a 44% growth rate. That's the percentage growth rate is 44% each hour. Each minute, it's 61% growth rate. So how can we change the model to represent the bacteria per minute? I know this seems like a little bit of a strange answer, but I think maybe that's the answer that we might be looking for here. And let me again, I told you I would do this. Let me go back to the standard for a second, and the thing we're trying to do. Today, the goal again is to produce an equivalent form of exponential expression to reveal percent rate of change. So is that what we've done here? Have we produced an equivalent form? That is this up here the same as this down here? In fact, it is, right? Because algebraically speaking, let's actually kind of show that that's true. If you have this, 2,000 times the 60th root of 1.44 to the 60t, which is what we have down here at the very bottom of the slide, is that the same as the thing we started with up in the box? You bet it is. Isn't this just 1.44 to the 1 over 60 to the 60t? And then multiplying exponents gives you this, doesn't it? If you multiply these two exponents, you get just 1.44 to the t, because 1 over 60 times 60 is just 1. So if you multiply the exponents up there, you do in fact get what we started with. So have we done anything? The answer is no, right? The two boxes the two things I've boxed on the screen are exactly the same model. So I know this is a little bit of a weird standard, but what we've done is it says, in the standard it says, what we want to do is change the model. We want to leave it be the same, but we want to have the model show what the growth rate is either by hour, 44% per hour, or by minute, 6.1% per minute. Okay, so sorry, lots of talking from me. I apologize. So if you haven't taken a crack at this one, give it a try. Notice the keyword decrease here. And then, yeah, so pause the video and we'll come back together in a minute. Talk with your table. Okay, are we back? Okay, so the list price of the car is $22,000. So let's call is maybe even as the last one. This time we'll use P. Maybe we'll use that as or how about V of T just for fun, for value of the car. All right, and it's 22,000 initially. So that's our like A value, and then we'd like to have something in here that represents what the model is, what the cost is, how it's decreasing each year by 10%, right? So what do we have to multiply something? This is the big question. What do we have to multiply something by to make it decrease by 10%? Now, careful with the wording there, right? Many of you will say, oh, we have to multiply 22,000 by 10%. And that will make it decrease by 10%. Well, no, not quite. If you want to mark things down in your store by 10%, it would be a grave mistake to take every price in your store and multiply it by 0.10. What does that give? I hear you say it gives 10% of 22,000. Okay, so then you say, oh, but that's not what I meant. I meant 22,000. Take that and subtract 10% of 22,000. And I agree that that will work. But there is another little bit of a slicker way to do it. And that's to say, could you do, instead of saying 10% off, what could you say? Could you say, I want, well, what percent of the original, what percent are you paying? If you originally were going to pay 22,000 and now you have a 10% discount, that's the amount you didn't pay is 10%. How much did you pay? What percentage did you pay? You didn't pay the 10%. You paid the, let me hear you say it. Yeah, that's right. I hear, good job, everybody. 90%, right? So maybe this is good. I have a question now. Is what you maybe suggested here, that this idea of the 10% discount, is that the same as just saying 90%? Are these two calculations the same? Yeah, I think they are. Can you convince yourself that these are actually the same? There's a chain of equalities as we go from left to right here that show that, oh yeah, actually that is the same piece of reasoning. All right, so have I convinced you fully that if you want to mark things down in your store, you should just go around and take all your prices and multiply them all by 0.9. I think that will do the job. So 0.90 there will do the job, I think, right? If you plug in t equals 1, you'll have, after 1 year, a decrease of 0.9%, you'll have a decrease of 10%, you'll have 90% of the original value. And if you plug in t equals 2, you'll be multiplying by 0.9 again and again and again. I think that will just make sense, I hope. Which results in what kind of behavior, just to tie things back together with some conversation we had the other day. Multiplying by 1.44 on the previous problem makes the function go uphill, you might say, increase. Multiplying as t increases by 1 each time, multiplying by 0.9 makes the function decrease, doesn't it? Multiplying stuff by 0.9 makes stuff get smaller. So I think we're in a good way here as far as doing this model doing what we think it should do. How can we change the model to represent the percent loss per day? Now keep in mind, this was each year, whoa, by 10%. Maybe I want to know like what the value of the car is on a particular day or in the middle of the year somewhere. It's a completely valid question. Again, I know it's a little strange, but we're going to just rock the standard here, try and go with it here. We would like to not change the model at all, and yet still somehow reveal the fact what the daily rate is. Okay, so if we decrease by, if we're talking about a 90% decrease, then what is that? What is that per day? What's the multiplier each day going to be? Well, how many days are there in a year? Let's call it 365. So we need a number that, if you multiply by this number 365 times, it's the same as just multiplying by 0.9. Well, I think by definition, that's the 365th root of 0.90. And then, just like on the last one, if we put a 365t up here, then have we done anything to this model? Just to be clear, we could have written it this way, too. 0.90 to the 1/365th to the 365t. Okay? Is it clear that we haven't changed the model at all? Well, now we have inside here, we have a daily growth rate. Now, just to be nice, I think that's not maybe how you might like to write it. You might prefer to write it this way. Let's actually take 0.9 to the 1/365th. Or on your calculator, you can do the 365th root. So I get, same number out here, times 0.99971 to the 365t. How do you like that? Does that look good to you? Okay. And then, so that's good. I think that's represent the loss per day. So the loss per day is, what is that? 0.03% decrease each day, which is not very much per day, but over the course of the year, that's a 10% decrease over the course of a year after 365 days worth of decreasing by 0.03% each day. All right, so what's the asymptote of this? We haven't asked you that question recently. It's the same function. You can look at this one up here, or you can look at this one down here. Any of the functions we've written on the screen, they're all the same function. What is the asymptote of this function? In fact, it's the only asymptote we've talked about. We haven't done anything other than this. The asymptote of these exponential growth and these exponential decay functions, in all cases, is y, I'll use y, hoping we know what we mean, is y equals 0. Or in this case, we might say v of t equals 0. So what does this mean? What does the asymptote suggest about what's going on here? What's going on with the value of the car as time goes on? What's happening to it? Go ahead, anyone? Anyone? Anybody? Anybody? Yeah. Yeah? You in the back? Okay, thank you. Yeah, that's right. The asymptote suggests here, it's not just kind of like a feature of the graph, it suggests that this is what's going on with the value of the car. The value of the car approaches 0. So I won't write that there, but you say something like that on your paper. Doesn't that make sense in the context of the problem? If it's decreasing all the time, every time it's 10% of what it, it's a 10% discount every year on what it was before, then it makes sense that it will never go away completely because you're eroding it by 10% each year. It'll never go away completely, but it'll ever more approach 0 in its value, $0 eventually. Now, from a practical standpoint, there will be a point where it actually reaches 0 maybe, because we can't keep taking like 10% of one penny or something. So there might be some practical constraints here. But from the pure math side of things, it makes sense that we have asymptotic behavior, doesn't it? Okay, last question, and then I'm going to let you loose on the other things that you have, the other worksheet that we have for you today. So if this is a model someone has already for the number of fruit flies in an experiment, and looks like Looks like it's growing, right? They're going up. Where t is the number of weeks, what's the growth rate per day? Great question. So first of all, I might ask, like, so what's going on here? Remember, this is like the multiplier, or the growth factor, the growth rate, whatever you want to call it. So I might say the growth factor, just from looking at the equation, is equal to 1.2. Oh, and by the way, before we get any further, what does the 7 indicate? Well, I think we can all agree that the 7 indicates that's the initial fruit fly population, isn't it? Population at like time equals 0, whatever, the beginning of our experiment. So that's seven fruit flies we're starting with, and then after 1 week we have 1.2 times as many fruit flies, and et cetera, et cetera. And after 2 weeks we have multiplied by 1.2 twice, 1.2 times 1.2 times 7 originally. Now there's one other thing we want to maybe identify too, and that's what the percent growth rate is, just for fun. Anyone see what that is from looking at it? What will that be? It's 1.2, so that's, again, like what kind of tip is that? If you multiply your bill by 1.2, I think multiplying by 1.2 gives us a 20% growth rate, right? Because again, think back to our equation that we started with earlier. It's inside there. It's like the initial amount, whatever it is, times 1 plus r to the t. So what's the r in our case here? Isn't it 0.2? Okay, well if it's 0.2, then by 0.2 we also mean 20%. Isn't 0.2 the same thing as 20%? That's what we mean by 0.2. 20%, same thing. All right, so I just wanted to kind of highlight what's going on with this model. Initially there are 7 fruit flies. We're growing by 1.2 times each time. So, all right, so what's the growth rate per day? That is, we need a number that when we multiply by this number, this unknown number, 7 times in a row, it's just the same as multiplying by 1.7. So what is this number, mystery number that if you multiply by it 7 times, it's just the same as multiplying by 1.2? Well, I think we all agree that it's whatever the 7th root of 1.2 is, or 1.2 to the 1/7 power, if you will. And I have that here written down. You need a calculator, I think, for this. I'm getting approximately 1.02, 1.026. See here, 39 if you want some more decimal places on that. Okay, great. So what was the question? What is the percent growth per day? So this is the growth rate per day. Each day you multiply by 1.02639. If you do that 7 times in a row, it's just the same as you having multiplied by 1.2. So what's the percent growth rate per day if you're just looking at the per day part? I think, if you can see it here, it's 2.639% per day. Notice that that isn't just 20% divided by 7, right? Or something like that. But we actually need to think about it in these terms. Again, I'm going back up to here to this original thought here. It's the 1 plus whatever the percent growth rate is here. And so here I think you can see it's the percent growth rate is 2.639%. Okay, I think I'm going to kind of stop there, and I do have the other problems up on the slide here. If you guys want to work through them, that would be great, and just kind of work together to solve those. Whatever you don't finish is, of course, your homework for tonight. Thank you guys for hanging out with me this period, and hopefully you have a great time learning some more about this new objective, revealing, using exponential models to reveal the percent growth rate. Let's just look at it one more time. I want to make sure I say it right. Have we done this? Have we been able to produce equivalent forms of exponential expressions to reveal percent rates of change? I hope that's something that you're able to do. It's still a very complicated idea, but I believe in each one of you. Have a great day, everybody.